Ciao to everybody. Therefore, I'm L.Ballerini. I'm a medical doctor in my back education, but I evolve as a scientist, or better as a neuroscientist, and I'm working in a neurophysiology lab since 30 years. My original place is Firenze in Italy, but since 17 years I'm working and leading a neurophysiology lab in Trieste, Italy. Carbon nanotubes are quite popular materials in nanotechnology. They are done from a sheet of graphite which is rolled up, and they are actually a tube. It's a tube of diameter 1-2 nanometers, therefore they belong to nanomaterials, and they are usually organized in scaffolds, three-dimensional scaffolds or small fibers, or actually tubes. Why so interesting, these materials? Because the material at these dimensions has extraordinary properties. A diameter of 1 nanometer means a dimension of 1 millionth of a hair. To visualize such small materials, you get to the electronic microscope, which is an instrument in which you can resolve the dimension of nanometers objects. At the microscope, a nanotube is absolutely similar as morphology due to its tubular shape to the smallest processes of neurons, which are neuronal cells, the cells of our brain, extensions, which provide the computational power of neurons. That means the way neurons operate with signaling. The idea of putting together carbon nanotubes and neurons to build up a hybrid system came from these morphological similarities. That means that the fact that at the microscope I cannot recognize what is a carbon nanotube and what is a neuron means that this similarity improves the ability of the material to get integrated to neurons. Since carbon nanotubes, among their extraordinary properties, are enriched with a huge electrical connectivity, and given that neurons communicate with basically electrical signals, we thought that the two things together might be of a certain use to promote future devices. For example, to improve neural prosthetic instruments, that means man-made materials put in the brain to collect or to deliver electrical signals, improving the way a neuronal network works. If carbon nanotubes are able to bypass neuronal signaling and help neurons in performing their activity, we might think that in the future that might help in rebuilding neuronal networks after damage, or improving neuronal performance without the damage due to loss of functioning in the elderly, for example. So recovery in a very long-term future, memory functions or neuronal ability which has got lost. For example, to describe the way carbon nanotubes are impacting on neuronal networks activity, I can describe what we have been seeing in cultured neuronal networks in vitro, so experimental conditions. As you all know, neurons communicate through connections which are called synapses. In the presence of carbon nanotube, this synaptic activity, the way messages comes from one neuron to another or goes from one neuron to another, are potentiated. Neurons are much more active. Synapses are much more active. The signaling is processed in a faster way. So being a medical doctor as an education, my straight view is towards recovery of lost function in case of lesions, or the most easy example is the spinal cord lesions, when there is an interaction in the transmission of the signal in our spinal cord, and this means that the part above and the part below a lesion is perfectly working, but they're not communicating anymore. So ideally, to find a system which might improve this communication by improving neuronal activity and connections, this would be extraordinary. So one of the possible future applications is engineering neuronal networks to recover function. But we have to say that why not thinking at improving neuronal functions, improving memory functions, although it's a more provocative, but it's something we have to deal with from an ethical point of view and from a scientific point of view as well. So if you're asking me whether I would, what I would prefer if I had to face a situation in which an implant might solve a problem in my brain function, I would be less afraid of an implant which I can take in and off than from a drugs which will slowly change in a chronic way the way my synapses work in a way which I can control only up to a certain stage. Of course, as any medication, is question of what is the risk and what is the advantage. If you're paralyzed and the possibility is to walk again, you go for it. If you just want to perform better to an exam, maybe you don't care and just study more. This is a neurophysiology lab, a typical neurophysiology lab, and what is in here is what is called a setup, which is all the machines and amplifiers and microscope which are needed to perform single neuron recordings. That means recordings the electrical activity from a single cell. Usually you need an anti-vibration table, like this one, because mechanical vibration will interfere with any recording. A microscope, because neurons are small objects, so you won't be able to visualize them without a microscope. A perfusing system which allows the survival, the viability of neurons for the entire time of recording. These are micro-manipulators which allow to put a pipette, the recording pipette, which is connected to the amplifier, which is here, and allow small movement of microns or less to approach the cell membrane. Then what is recorded in here usually gets to the amplifier in here and then to the computer where the electrical signal is recorded upon amplification. One of the great advantage of the recent developments in nanotechnology is that this discipline has forced the merge of different disciplines. What I mean is that to deal with nanotechnology scientific problem or technological problem imply that scientists with different background, a medical doctor as I am, or in organic chemistry, as one of my major collaborators, Maurizio Prato, are forced to talk to each other. And it's not obvious that we're using a common language to start with. At the beginning, we couldn't understand each other, and the first year was spent in useless discussion. At the end, after 8 years of complementary work, we can easily get into the problem of one or the other with our own experience and expertise. So somehow we've been breaking the barriers which usually divide one discipline, chemistry, from the other, mathematics or physics or biology. And this is a great advantage for scientists. I'm convinced that this is extremely important for the science of the future. We need to clarify one crucial point. When you're involved in basic research, you work on subjects, on ideas, on possibilities which are not directly linked to a clinical application. That means that these subjects or research topics are not an immediate have not an immediate application to cure a disease. There is a gap between these two things, which takes a long time, but nevertheless, there is a perspective. When you're doing basic research, you are convinced, and I am, that altogether we will bring important breakthrough for future applications. The point is when. We don't know when this will be available, but still there is the great belief that whatever we are doing is in the perspective of ameliorating human conditions.